world is impossibly old, bathed in the dim, ruddy light of a star long past its prime. Here, on the shores of a sea not of water, but of sluggish cryogenic methane, a living thing begins to stir. It is not a stir of muscle and nerve, but of slow, deliberate crystallization, a towering, faceted spire of a creature, its body a lattice of silicon and oxygen, groans with a sound that is not a voice, but the resonant frequency of stressed crystal. For a century it has remained motionless, drawing faint energy from geochemical gradients in the frozen rock beneath. Now it must move. With agonizing slowness, covalent bonds at the base of its structure are chemically persuaded to break, while new ones are formed nanometers away. The motion is less a step and more a controlled geological shift. An appendage, a crystalline blade several meters long, grinds forward, leaving a gouge in the nitrogen ice shoreline. The air, thick with hydrocarbons and bereft of free oxygen, carries no scent a human could recognize, only the cold, sharp odor of fractured minerals and complex silanes. Its thoughts, if they can be called that, are not the rapid electrochemical pulses of a brain, but the glacial propagation of patterned impurities through its solid-state body, a calculation that takes years to complete, deciding its next 100-year-long action. This is life, but life pushed to the very edge of its definition. It is rigid, it is crushingly slow, and its every metabolic process is an uphill battle against an unforgiving, low-energy chemistry. It is life as a geological process. Looking at this monumental frozen struggle, we cannot help but ask a fundamental question. Is this extraordinary exception the rule, or is the fluid, rapid, warm, and chaotic dance of life on Earth the true cosmic standard? To understand why our familiar biology might be the universe's default, we must first distill life down to its most basic requirements. Life is not merely a collection of chemicals, it is a process. It is a system that can sustain itself, replicate, and evolve. To do this, it needs a few non-negotiable components. First, it requires a solvent, a liquid medium where the molecules of life can meet, interact, and assemble. For us, this is water, a substance with a remarkable capacity to dissolve other compounds and stabilize temperatures. Second, life needs a way to store information, a blueprint, for its construction and operation. On Earth, this is the elegant double helix of deoxyribonucleic acid, DNA, a molecule capable of holding vast libraries of data in a stable, replicable format. Third, life needs a mechanism for metabolism, a way to capture energy from its environment and use that energy to build and maintain itself. And finally, and most crucially, life needs a structural backbone, an element versatile enough to build the complex machinery required for all these other tasks. It needs an atomic Lego block that can form chains, rings, branches, and scaffolds, creating the vast molecular architecture of cells, tissues, and organisms. Across the 118 known elements in the periodic table, only one proves uniquely, almost preternaturally, suited for this structural role: carbon. Its supremacy is not an accident of terrestrial history, but is seemingly written into the laws of chemistry itself. Carbon is the fourth most abundant element in the cosmos, forged in the fiery hearts of stars and scattered across the galaxy by supernovae. Its availability is a prerequisite, but its true power lies in its atomic structure. A carbon atom possesses 4 valence electrons, meaning it has 4 hooks in its outer shell available to form covalent bonds with other atoms. This perfect quartet of bonding sites is a key to complexity. With 2 or 3 hooks, you can make chains. With 4, you can build in 3 dimensions. creating the intricate tetrahedral geometry that allows for complex, functional shapes like the active sites of enzymes or the intertwined strands of DNA. But it's the nature of these bonds that sets carbon apart. The carbon-carbon bond has a Goldilocks quality, with a bond energy of around 348 kilojoules per mole. It is strong enough to create stable, long-lasting molecules that won't just fall apart at room temperature. Yet it is not so overwhelmingly strong that it cannot be broken and reformed by the relatively gentle persuasion of biological enzymes. This delicate balance between stability and reactivity is the very engine of metabolism. It allows a living cell to construct what it needs and then deconstruct and recycle those components when they are no longer useful. Furthermore, carbon has an unrivaled ability called catenation, the capacity to link with itself, forming incredibly long and stable chains. It can create polymers stretching to millions of atoms in length, a feat no other element can approach with such stability and versatility. It also forms single, double, and triple bonds with ease, allowing for rigid, planar structures or flexible rotating chains, adding another layer of architectural diversity. From the fatty acid tails of our cell membranes to the polypeptide chains of our proteins, this unique talent for self-linkage is the foundation upon which all known biology is built. In this atomic toolkit, carbon is not just one option among many. It appears to be the master key, an element seemingly designed to be the scaffold for living matter. The universe is filled with it, and its chemistry is a symphony of creative potential. The question then is whether any other element can even come close to conducting a similar masterpiece. In the quest for an alternative to carbon, science and science fiction consistently converge on a single candidate. Located directly below carbon on the periodic table, it is a tantalizing prospect. Like carbon, it possesses 4 valence electrons, suggesting it too can form a rich and complex chemistry. Silicon is also fantastically abundant. It makes up nearly 30% of the Earth's crust, locked away in rock and sand. For a planet-bound biology, silicon is far more accessible than carbon. On paper, it looks like a worthy rival, a parallel path that life could have taken. Yet, when we move from the periodic table to the practical realities of biochemistry, the silicon dream begins to fracture, revealing fundamental flaws that carbon elegantly avoids. The first and perhaps most significant problem is one of size and stability. A silicon atom is larger than a carbon atom, its valence electrons residing in a higher energy shell further from the nucleus. This increased distance results in longer and weaker bonds. While the carbon-carbon single bond is a robust 348 kilojoules per mole, the silicon-silicon bond clocks in at only around 226 kilojoules per mole, a full third weaker. This difference is not trivial. It has cascading and catastrophic consequences for building complex molecules. While carbon can form near-infinite chains, creating the stable backbones of polymers like plastics, proteins, and DNA, silicon's ability for catenation is severely stunted. Chains of silicon atoms, known as silanes, become progressively less stable as they grow. A silane with just a few atoms is already highly reactive and pyrophoric, spontaneously igniting in the presence of oxygen, getting them to link into long, stable polymers akin to what carbon does is, for all practical purposes, a chemical impossibility under conditions that could support life. Furthermore, silicon struggles to form the double and triple bonds that give carbon chemistry so much of its structural diversity. The large size of the silicon atoms makes the orbital overlap required for these multiple bonds energetically unfavorable. This eliminates a vast swath of molecular architecture that is fundamental to our own biology, like the rigid ring structures in DNA bases or the functional groups in amino acids. Silicon chemistry is, in essence, a pale, structurally impoverished imitation of carbon chemistry. Even if one could somehow stabilize long silicon chains, a second, more immediate obstacle emerges: the problem of a solvent. Life as we know it is an aqueous event, playing out in the theater of liquid water. Water is often called the universal solvent for good reason. Its polarity allows it to dissolve a vast range of substances, ferrying nutrients and waste products throughout a biological system. For carbon-based life, water is the perfect partner. For silicon-based life, it would be a universal destroyer. Solanase and many other silicon compounds are unstable in the presence of water. They are rapidly hydrolyzed, a chemical reaction where water molecules break them apart. A silicon-based creature emerging in a watery world would simply dissolve. This forces us to imagine silicon life on a world without liquid water, turning to alternative solvents. The most commonly proposed are cryogenic liquids like methane or ethane, which exist on moons like Saturn's Titan. But this solution creates another insurmountable problem: temperature. Liquid methane exists at a chilling -161 degrees Celsius. At such profound cold chemical reactions, slow to a geological crawl. As a rough rule, reaction rates halve for every 10 degrees Celsius drop in temperature. The metabolic rate of a hypothetical creature on Titan would be thousands, if not millions of times slower than that of an earthly microbe. Life would exist not on a timescale of seconds and minutes, but of centuries and millennia. Evolution, the very engine of adaptation, would slow to a near standstill. Could a complex ecosystem ever arise under such kinetically throttled conditions? The energy available to drive metabolism is also vastly lower in such environments, placing another severe constraint on the potential for complexity. Other potential solvents like liquid ammonia or sulfuric acid each present their own unique and devastating set of chemical hurdles, from extreme pH to a tendency to break down complex molecules. But perhaps the single most damning argument against silicon-based life is the problem of breathing. For any active, mobile organism, metabolism requires a continuous exchange of matter with the environment. We take in complex carbon compounds, food and oxygen, for respiration, and we expel the waste products. For us, the primary waste product is carbon dioxide, CO2. The genius of carbon chemistry is that at the temperatures where water is liquid, carbon dioxide is a gas. This makes waste disposal incredibly simple. A gas can be effortlessly exchanged with the environment through lungs, gills, or simple diffusion across a cell membrane. It's a clean, efficient, and elegant system for shedding metabolic byproducts. Now, consider silicon's equivalent. When silicon is oxidized, the byproduct is not a gas. It is silicon dioxide, SiO2-, better known as sand or quartz. It is a solid crystalline rock. A silicon-based creature that respires by oxidizing silicon compounds would be faced with the monumental task of exhaling a solid. Imagine every cell in your body producing microscopic grains of sand as a waste product. How could a biological system possibly function? It would need an impossibly complex and energy-intensive mechanism to constantly collect and excrete this solid waste from every part of its body. Failure to do so would lead to rapid internal petrification, The organism would literally turn to stone from the inside out. Some have speculated that such a creature might use a fluorine-based respiration to produce gaseous silicon tetrafluoride, but fluorine is an extremely reactive and relatively rare element, making it an unlikely basis for a planetary-scale ecosystem. This single stark chemical fact, the solid state of its oxidized waste, may be the ultimate checkmate for silicon-based complexity. Carbon's gaseous oxide allows for the dynamic, flowing exchange of matter that active life requires. Silicon's solid oxide dooms it to a world of geological slowness and irreversible petrification. When we analyze the contenders, it's not a close race. Carbon's atomic properties give it a combinatorial advantage that is not just orders of magnitude greater, but fundamentally different in kind from any other element. The verdict on silicon may seem definitive, but is this certainty a product of sound chemical reasoning, or simply a failure of imagination, a form of carbon chauvinism? This question pushes us into a deeper philosophical and scientific territory, centered on a concept known as the anthropic principle. In its weak form, the principle is almost a tautology. The conditions we observe in the universe must be compatible with our own existence. We find ourselves living in a universe that supports carbon-based life, because if it didn't, we wouldn't be here to observe it. This could mean that countless other universes exist with different physical laws, and we just happen to live in one of the few where the chemistry is right. But it could also mean we are just provincially attached to our own biology, unable to conceive of truly alien life forms. Perhaps we are looking for the wrong things. Our entire framework for astrobiology is built around carbon's preferences. We search for exoplanets in the habitable zone, which is defined as the orbital distance where a planet's surface temperature allows for the existence of liquid water. We scan alien atmospheres for biosignatures like oxygen, methane, and carbon dioxide. This entire search strategy presupposes that life elsewhere will be, at a fundamental chemical level, like us. It's a practical assumption, but it could be a profoundly limiting one. If silicon life exists in a cryogenic methane sea on a distant moon, it would not produce a whiff of oxygen. Its metabolic byproducts might be solid precipitates that fall to the sea floor, never reaching the atmosphere to be detected by our telescopes. Its slow geological existence would be utterly invisible to a search paradigm focused on the rapid, gas-exchanging chemistry of carbon. We could be staring right at a living world and failing to recognize it. However, the counter-argument is that the unique advantages of carbon are not a local phenomenon. They are derived from the universal laws of quantum mechanics and thermodynamics, the bond energies, atomic radii, and electronegativity that make carbon so versatile and silicon so comparatively flawed are the same everywhere in the cosmos. Water's properties as a solvent and the solid state of silicon dioxide are not matters of opinion. They are fundamental physical realities. To argue for viable silicon life is to argue for a system that can overcome truly monumental chemical and thermodynamic hurdles. While it is unscientific to declare it impossible, it is reasonable to conclude it is profoundly improbable. The universe is incredibly vast, but it is not infinitely permissive. The laws of chemistry create a set of rules, and these rules appear to have a strong favorite. This understanding also reshapes our own connection to the cosmos. The carbon that makes up our DNA, our proteins, and our brains was not created on Earth. It was forged deep within the cores of stars long dead through a delicate nuclear reaction called the triple alpha process, where 3 helium nuclei are fused into a single carbon atom. This precious element was then violently ejected into interstellar space by supernova explosions, seeding the gas clouds that would eventually coalesce to form our solar system, our planet, and ultimately, our bodies. We are, in the most literal sense, made of stardust. This isn't just a poetic phrase. It is a statement of our precise chemical origins. Our existence is inextricably linked to the life cycle of stars. This cosmic narrative suggests that carbon-based life may not be an accident, but a predictable, perhaps even inevitable outcome of stellar evolution. When stars create carbon, they are manufacturing the very seeds of complexity. In a universe governed by entropy, a relentless slide towards disorder, carbon's unique ability to build stable, complex, information-rich structures represents a powerful local countercurrent, a chemical pathway for order and complexity to emerge from the chaos. Thus, our dominance, and carbon's, may not be a sign of our limitation, but rather an insight into the fundamental logic of the cosmos. The search for life becomes less about finding bizarre exceptions and more about understanding the prevalence of a universal pattern. We are not just looking for life. We are looking for other instances where the universe has expressed its inherent potential for complexity through the versatile chemistry of carbon. It's a search for our chemical kin across the vast, dark expanse. Ultimately, asking why carbon leads us to a more profound question: why a universe that so perfectly accommodates carbon? The special properties of the carbon atom are not an isolated fluke. They are a direct and sensitive consequence of the fundamental constants of physics, the precise values that govern the entire cosmos, such as the strength of the strong nuclear force, the weak nuclear force, the electromagnetic force, and the force of gravity. If you were to minutely alter these values, the universe as we know it would cease to exist. Consider the triple alpha process, the stellar forge that creates carbon. This process is exquisitely sensitive to the strength of the strong nuclear force. If this force were just 0.5% weaker, the resonant state of the carbon-12 nucleus wouldn't exist, and stars would be unable to fuse helium into carbon. The universe would be a simple place, made almost entirely of hydrogen and helium, devoid of the elements needed for planets, let alone life. If the strong force were slightly stronger, helium would fuse so rapidly that stars would burn out long before life could have a chance to evolve. The very existence of carbon in abundance is a testament to an astonishingly fine-tuned physical reality. This extends to carbon's chemical behavior. The strength of the electromagnetic force dictates the behavior of electrons, and thus the nature of chemical bonds. A slight change in its value would alter the Goldilocks strength of the carbon-carbon bond, perhaps making it too weak to form stable life, or too strong for metabolism to work. The entire edifice of biochemistry rests upon a knife's edge of fundamental constants. The revelation, then, is not merely that carbon is a superior building block for life compared to silicon. It is that the universe, through its fundamental and unchanging laws, appears to be constructed in a way that singles out carbon. Its dominance is not a simple matter of chemical competition on planetary surfaces. It is a reflection of a deeper cosmic architecture that makes carbon the nexus of complexity. In this view, carbon-based life is not an improbable accident. It is the natural, perhaps even inevitable, expression of the physical laws of this specific universe. The question of whether other life exists is transformed. We are no longer just looking for a biological counterpart. We are investigating whether the deep structure of reality itself, allows for more than one way to create the intricate phenomenon we call life. All the available chemical and physical evidence suggests that while the forms life might take are fantastically diverse, the fundamental chemistry underpinning it all will be the same here as it is a billion light years away. It will be the chemistry of the fourth most common element in the universe, an element forged in stars and endowed by the very laws of physics with the unique power to awaken the cosmos to itself. The universe isn't just hospitable to carbon-based life, it seems to be built for it.